this talk is divided into parts also because it has really two different topics. One is an introduction to compiler technology and compiler construction, and the other is more advanced and will be a talk on MLIR, which is let's say the frontier at the moment of compiler construction, I would say. Now, 1 hour to introduce compiler construction is really a challenge. So I will try to go through as many of the steps the compiler does in as little time as possible, but we'll see what we manage to do. So, obviously here we are in an environment of people involved in HPC, so for you it's clear why compiler technology is needed for performance. The idea is that a naive implementation of the compiler can lose quite some performance. Okay. It is also notable that performance reflects on resource usage, so there are also concerns on, say, inefficient compilers leading to higher resource usage, energy usage, and so on. That said, what exactly is a compiler? A compiler is a tool that translates from two different languages. No, it translates from a source language that is human readable, or let's say it's primarily human readable, to a target that is primarily machine readable. It does so through a series of different transformations, which are partly very formally defined and partly very informally defined. It can be seen as divided into three different stages: the front end, the mid end, and the back end. What is the real divider here? The front end covers all the technologies that are primarily source language dependent. The backend covers technologies that are primarily target, so machine dependent, and the mid-end covers optimizations that are somehow abstract with respect to the target architecture and also from the source language. So they can be performed on something that is not the initial language or the final language. This imposes that there must be something in the middle, okay, an intermediate representation that represents the same semantics as the original program, but without all the syntactic sugar that is typical of source languages, and also enables the production of the target language, but once more without the peculiarities, the idiosyncrasies of all the different possible architectures. The goal of this partition is to create in the mid-end a core of functionalities that can be used to perform the translation not only, let's say, from C language to IR and then maybe x86, okay, assembly. That would be a compiler. It compiles through these stages. At some point, you might want also Fortran. Okay. At some point, you may also want ARM or RISC-V or whatever else. And here also in the source side, the number of potential languages that you might want to translate is very high. Okay, consider what would happen if we had to build a front end, mid end, and back end for each combination. It would explode. This solution of having an intermediate element that serves as a common point between different source languages and different target machines reduces significantly the complexity of building compilers. Okay, so this partition is imposed by the need to minimize the effort. This minimization of effort is extremely important. Why? Because developing a compiler takes more or less 200 years. Okay, that's an estimate that is reasonable for the majority of compilers until getting to, I would say, like 5% of the performance of GCC. Okay, so it is an extremely costly effort and must be organized in this way to minimize this effort. So what actually goes into the front end? No? The front end happens here, and here we have the back end. Whereas the mid end is typically something that circles over the intermediate representation. Once more, this solution makes it so that I have to build a front end for each language, but that's unavoidable, a back end for each target, and that's fine, but all the mid-end solutions are recycled. I just select those that are appropriate for my particular toolchain. Then what is inside the front end? Inside the front end, we have, once more, multiple steps. In the first place, we need to consider that a programming language is composed of words. Okay, it's a language, so it's composed of words that are built together into sentences. Now, going into the full details of how this is the recognition of a language is performed is beyond the scope of a talk like this, but we can remember that a language, the words of a language, of a technical language, so programming language or a data representation language, are typically embodied by regular expressions. So it can be either fixed words, like the keywords of a language, while, for, whatever, or there in the slide you can see the typical representation of a C-like identifier, and the representation of typical numbers, integers, and floating point numbers, or real numbers, okay, that you could find in a language. They are not very general. For instance, identifiers in Python, they accept also Unicode characters, not just ASCII, like in this case, but they are sufficiently general to give an understanding of what is going on. This kind of recognition is performed through FSAs, finite state automata, which basically are a very, very simple theoretical structure to model computation, and produce out of your source code, which is per se a file composed of characters, it produces a stream of tokens, so words in the language with their actual value. So for a number, it would be number plus the value of the number. Once you have the stream of words, you want to recognize, you need to recognize the syntactic structures, so the sentences of the language, how they were produced from the grammar of the language. A grammar is a more complex language structure. It's called a type 2 language in Chomsky categorization, which is basically a language that is able not only to recognize iteration as it's possible already in regular expression, but it can also recognize parenthetical nestings. Okay, if you consider a programming language is composed mostly of words that are grouped together through parenthetical structures, which can be actual parentheses, braces, begin-end constructs, these kind of things. So these elements are necessary to recognize the structure of the program, and therefore we need recognizers for a type 2 language. Here we see the simplest possible type 2 language, the big language with a single set of parentheses. There are many possible solutions to perform the actual parsing. What is currently used in practice is mostly a top-down recursive descent predictive parser. What does it mean? It means that we take the rules of our language, which define basically the expansion of let's see if I have I have a slide for that. it takes the expansion of a non-terminal, so a letter that is not part of the actual language. Here we have the same Dick language. It is defined as S, the axiom, so the initial non-terminal, which is replaced by any number. Star means an iteration, an unlimited iteration, of what? Of parentheses that include recursively another instance of S. The unlimited iteration can be 0, so it can also be the empty string. What does this define? It defines nests, arbitrary nests of parentheses. So the string couple of parentheses is part of the language. Few nested parentheses are part of the language. They are obtained how? Well, S goes into a single brace and then a single set of braces and then another S, and then this S is also expanded into this, and finally the last S is expanded to empty. Okay, so these constructions recursively expand to produce all possible valid strings of the language, and therefore all possible programs if this was the grammar of a programming language. Okay, the problem, however, is the reverse. We need to recognize the structure that generates the language. So this production can also be seen as a tree, okay, where we have these elements, and here we also have, and then epsilon. Okay, so by this structure you would be able to recognize, for instance, if this was the rule of a real language, it would be something like if open parenthesis, then condition close parenthesis. I would need to recognize that this condition is generated as part of this if construct. This is still a parenthetical construct, and I need to build if, okay, the parentheses are really only syntactical element, but I need to build this tree. Okay, how can I do so? Well, what I employ is, or what we employ actually is, as I said, a top-down predictive parsing that is simply derived from the grammar itself, as long as some rules on the grammar are respected. In particular, if you look at this S that goes into parentheses and S and so on, we can we consider that this is a recursive rule, no? So we will need a function call that can be recursive. So each non-terminal becomes a function call, or really a procedure that is then called inside other procedures. These elements are mandatory elements. They are fixed words. So I need to, when I try to recognize S, the axiom, I need first to read an open parenthesis. Or, since this is completely optional because there is a star, I could also read nothing. Okay. So either the string is empty, or I need to read one of these parentheses. So it's if there is a parenthesis, I do something else. What is the something else? Is I go on and I call S itself. And then after the return from S, I will need to find another element of the closing type, let's say. Since I have the star, I have 0 or more iteration, this becomes a while, so I just loop over this operation until the end of the string. So in a nutshell, this is how the front end is built. There is just one more element, there is semantic analysis. The reality is that parenthetical structures are unfortunately not sufficient to represent programming languages. All programming languages have context-sensitive features. What does it mean? We consider context-free a language element that can be understood at the level of the individual rule. Like in this case, the pair of parentheses is determined regardless of what is the content of the pair. So I can, after understand or after opening this parenthesis, I can recognize independently the content of S, and then afterwards I just check the remaining elements. This is true also, of course, in equivalent elements in programming languages, but there is one typical element that escapes from this notion, that is type checking. When you have, for instance, in C, variable declarations, they are used after the declaration. That's fine, because otherwise you could not check. But they can be used very far from the declaration. Okay, so it is impossible. It can be proved to be impossible to perform the type checking within the type of construction that we have just shown. So some other mean must be employed to perform these checkings. How it is done? Well, typically what you have is that in your program, the declaration must precede the use. So what you will do is to store the declared variables as soon as you declare them, taking into account the scope of variables, and then check that every use is a use of a known variable. But this is performed outside, let's say, the structure that we just saw. So there is a formalism for it. This is called attribute grammars, but it's less powerful and less simple to implement than the parsing. Still, these three elements compose the front end, and they produce essentially what as the output? They produce a tree like this that is decorated with additional information. For instance, there may be pointers to the declaration of variables in their use. So this allows you to have a bit more information. Then, after this construction, we need to move into the intermediate representation. An intermediate representation can be the tree itself, okay? But usually this is not a very effective representation. Why? It is a one-to-one map of the source language. And we said that we want actually something that is at an equal distance from the source and the backend and the target language. Okay. Furthermore, some of these constructs are obviously very high level. They represent elements that are not part of the target construction. We can see in the slide an example of such a tree where we have a plus b that is parsed into a very simple tree where we have a node that loads variable a node that loads variable b, and a node that performs the sum. Okay, the sum per se would be a simple operation that can be translated directly to assembly. However, the load is not, because that read the value of a can be something different depending on where in memory a resides. And if a is in main memory, let's say it's an automatic variable, then the translation is what we see here. Okay, so it's an access in memory with a binary operator that performs the sum of the base pointer, which will be the frame pointer in this case, plus a constant offset k. This translation from the single node that performs just an access to an high-level variable to something that operates with actual memory addresses, or at least abstract memory addresses in this case, is called a lowering. Okay, it's a phase that moves from an intermediate representation that is very near to the source to one that is nearer to the backend. This lowering can be performed in different phases, so it can be performed all at one time, where you move most of the constructs from the high level to the very low level, or in different stages. This will be important later on when we look at MLIR, because that's exactly how MLIR does it. The intermediate representation. The intermediate representation is really so the main one, the one that is used for most of the optimization, is really the main engineering challenge in building a compiler, in designing a compiler. Indeed, if you consider LLVM, LLVM is the name of the intermediate representation. Why? Because the compiler framework is actually mostly a library for working with intermediate representation. LLVM per se doesn't even have a front end. Clang is a different project in some sense. So how do we design intermediate representations? Well, luckily someone typically designs it for you because these are huge projects that require a lot of manpower, so someone else will have done for you. But the main principles that are used in this context are the ease with which you are able to perform the transformations and the analysis of the code, and the ability to represent equally well front-end languages and target assembly languages. What is considered nowadays as the best solution, or at least a very useful solution, is static single assignment. Static single assignment is a class of intermediate representations where you could say that the values of temporaries, let's say, are assigned only once. Statically, so they can be assigned multiple times at runtime, but not in the code. So there is a single point in the code where each value is produced. Why is this useful? Because it allows you to represent values with the instructions that produce them. So inside the compiler, a value can be identified as the pointer or address of the instruction of the intermediate representation that generates it. This simplifies a lot a number of analysis, and therefore, for instance, LLVM is fully using static single assignment up to the very end of the process, so until basically register allocation, whereas MLIR has an intermediate solution because of other reasons that we'll see. So what happens when we need to perform optimization? Okay, which optimizations? Well, I will start with register allocation. Why? Because really it's a mandatory step. You could do a very, very trivial register allocation, but it would lose a huge amount of performance. Why? Because fast memory is really the scarcest resource in a machine. The fastest memory is the register bank itself. The register bank is typically very small, it has only a few elements. Obviously, you could allocate all variables in memory and just load them into a register when you need to perform an operation. However, this is extremely small because it causes a vast amount of traffic between the CPU and the main memory, or at least the cache. So what is typically done is trying to put as much stuff as possible in the registers, even if the principle is that when you declare a variable in the program, then it gets allocated into the stack. This is not always true. The compiler tries to promote from memory to register, so to avoid storing variables in memory. This is obviously effective at improving performance, because if you have space in the registers and you don't store a variable in memory, then you have saved a number of load store operations that, as you all probably know, are slow with respect to arithmetic instructions and unpredictable because of the cache hierarchy that leads load store operations to be difficult to predict in time. However, this creates another problem. The more I promote variables from memory to registers, the more pressure I put on the register bank. Typical program has active at the same time between 3 and 10 variables. But if you start promoting aggressively, this can increase significantly. So you may have more variables in registers than actual registers that you have. To address this, the compiler tries essentially to decouple the problems. So it uses virtual registers in the intermediate representation. Virtual registers means that every variable is assigned a new register as if the machine had an unlimited number of registers, and then these virtual registers are mapped to physical registers. This mapping, unfortunately, is an NP-hard problem. So it's computationally unfeasible. In an optimal solution cannot be found in a reasonable time frame. So what can you do is to use one of several good heuristics that have been developed in time. Okay, the idea that is exploited is, okay, you have all these virtual registers, but not all of these values are needed at every time. No, some of them are only useful between the point where they are generated. The value is generated when the instruction that computes it is performed, and the point in the code where that value is used. Okay. If there are no other uses afterwards, the value is considered dead. Okay, so it's not useful anymore. If two values have completely non-overlapping intervals between their first definition and last use, then they can reside freely in the same physical register because they are never alive at the same time. Okay. Once more, as I said, the problem is intractable, but there are two good algorithms to address it. One is the linear scan, which is the one that is implemented, if I remember correctly, in LLVM, and the other is more traditional one, the graph coloring. The graph coloring, it's interesting because it has a very simple explanation. It basically considers the virtual registers as a number of as countries in a political map. Those that are they interfere are considered neighbors, and you try to color the political map with as many colors as you have physical registers. If you remember the maps in elementary schools, those have different colors for neighboring countries to distinguish them. Okay, assigning these colors is a problem that has been studied in operations research for a long time. So there are standardized solutions that you can use, which are polynomial, not very low polynomial, but still polynomial, and produce excellent results. Then, once you have allocated your registers, you need to move from the intermediate representation to the actual machine instructions. So this is clearly something that depends on the particular instruction set, and there are several solutions. Okay, one is the simple one is the one that is used for most RISC machines. RISC machines are characterized by having very simple instructions. So the semantics of each instruction is very simple. So it is likely that the majority of IR instructions are either mapping already one-to-one, like a sum. It's a sum also in the target instruction set architecture, and in the IR it will be probably a sum between registers, between virtual register, but you have already performed register allocation, so you are fine there. So you can just map one-to-one. Or you may have instructions that are a bit more complex than what you would find in an actual ISA. So for instance, the function call in the IR typically already abstracts the prologue and the epilogue that you need to insert to deal with the ABI. Okay, so there you just have a snippet of code that you need to insert at a point. So what is done is typically to use a tabular approach to code generation, where you have a list of IR instructions and a list of corresponding fragments of code, where you only need to replace the operands with the correct registers and memory locations. And that's all. However, for more complex architectures, like CISC architectures, x86, this may be suboptimal. Okay, so there are also other algorithms that are used to generate instructions out of multiple IR instructions. So try to cover a group of IR instructions with a single instruction of the target assembly. In this case, the problem is once more complex. There are several algorithms that can be used, in particular the maximal manch algorithm. What it does is basically performing something like this. It starts from, for instance, here we have a memory access, here you have a temporary value, and here I also have another memory store. Okay, and here this memory access need to have a computed so frame pointer and a constant. Okay, this performs a load from the main from the stack, sums the value of variable that is in a temporary, so in a register, and then stores back the value. This could be like something like a plus I, where I is the index of a loop. Okay, the index of a loop is typically promoted from memory to a register. So what does the maximal manch do? It looks at the root of this tree, okay, and tries to find the largest instruction that from the instruction set architecture that covers most of this tree. Okay, maybe it finds just a store, but maybe it finds something that is a sum that also that has the ability to store the result not in a register but in memory. Okay, so if it is a CISC architecture, that's a possibility, and so on. You might have even an operation that performs a sum from a register on a memory location, and then if these two memory locations are the same, then you can use this particular instruction. Okay, so this tries therefore abbiamo un problema. So it basically tries to cover as much of the tree as possible. That's why it's called maximal manch. After you have covered part of the tree, the remaining subtrees are recursively covered in the same way until you get only empty trees. This is greedy, so it doesn't look ahead a lot, therefore not optimal. But if you can also do the reverse, so start constructing optimal solutions for each leaf node. Like for a constant, you have typically to perform some move or load instruction. For frame pointer, you have to do nothing, and so on, until you find intermediate nodes. There you look at the solutions for the subtrees, the solution for the individual node, and any possible solution that covers more than just this node, and you perform the sum of the cost of these solutions and find the optimal one. What is the cost? Typically is the number of instructions, or you may have other metrics like the execution time if you're able to devise this. Note that the interactions of register allocation with instruction selection are non-trivial when a single instruction can generate more than one instruction, because in that case you might need additional registers that you don't have typically. So you may have to cycle through or to clobber a register. It means to move the value in memory and then pull it back after you have used this register. This is also the reason why sometimes you have a scratch register that is actually not used in allocation. Okay, let's so now we have a picture of the whole compiler, except we haven't optimized a lot. Okay, so let's try to see what can be done in terms of optimization. So the theory is that you would put the machine-dependent optimization into the backend, where you have all the information about the target, and in the mid-end, all the machine-independent optimization. The reality is that there are very, very few things in a compiler that are fully machine-independent, including the front end. For instance, consider the C language, okay? The definition of int is machine dependent. So really, the compiler is machine dependent from the beginning. How does therefore this still hold? Well, typically what you have is that the amount of information that you need from the target is relatively small. You can build a parametric front end that takes a target information data structure as the parameter, and where it contains typically this kind of data, such as the size of int, the natural size of int, and so on. For optimization, we have the same, except that here the target data that we typically need are things like cache size, memory size. It goes as far as an entire model of the pipeline, but there you are already very machine dependent. So with this caveat, let's look at optimization. One issue first, correctness of optimization. What does it mean for a transformation to be correct? Well, typically we would like that the source language and the target program, the source program and target program have the same semantics. So they do the same things, but the source program actually does nothing because it's not directly interpreted. Okay, so if we have an idea of what it should do, but there are some conditions under which it is not exactly clear how the program should behave. For instance, when we perform transformations on the code, we may change the exception behavior. What happens if your transformation removes a division, and that division could divide by 0? Obviously, you have removed an exception from the program. The same is true for the commutative and associative properties of instructions or of operations. So you have the sum operation. This operation is supposed to be commutative and associative, but actually this is true in arithmetics, not in floating point arithmetics, where the commutativity and associativity of instructions are not fully supported. These instructions are considered semi-associative and commutative. So, what is the meaning of correctness that we assume? Well, we typically assume that all results of semi-commutative operations are equally valid. Okay, so we can reorder freely even if the results change. and that we expect semantics to be the same, so to produce the same result when there are no exceptions. Okay, so we can produce something different if the original program produced an incorrect result. These relaxations of the semantics are needed in order to be able to perform some transformations, and are really the minimum. The majority of compilers don't even fully implement the semantics of the source language. So if you consider GCC, it doesn't really pass all the tests. In some very, very small corner cases, it doesn't implement the semantic of C. So there is a trade-off between optimization and being fully compatible with the semantics of a program. There are a number of transformations that are flagged as not respecting the semantics, and which can be disabled explicitly. In particular, when you go to -03, you may be enabling some transformations that are not exactly respectful of the semantics in some corner cases. So the topic of compiler transformations for optimization would require me around 4 hours, but we only have like 15 minutes or so. So I will try to give you an idea of what are the primary categories of compiler transformations. Well, first of all, where they are applied. Okay, we can apply transformation at several different scopes. The larger the scope, the higher the opportunity for optimizing. The smaller the scope, the faster the process is, but smaller the gains. The real scenario is that we almost never perform interprocedural optimization, so optimization between code of different procedures, because it's very costly to perform the analysis. But we will see that there are some transformations that allow us to cheat and do some interprocedural optimization. So sort of overview of optimizations. Data flow-based loop transformation. This is a category of transformations that try to optimize the behavior of loops by taking advantage of the fact that some of those computations are really not that loop dependent, or they are performed implicitly. Part of them can be performed implicitly by the loop itself. The typical example, aside from loop invariant code motion, which just takes a loop invariant and computes it first outside the loop, is loop-based strength reduction. Loop-based strength reduction is essentially a transformation that takes an operation that computes the same value multiple times and reduces its strength by reusing the old value that has been computed in the past, in the previous iteration of the loop. For instance, if I compute x times I, where I is the index of the loop, okay, and I compute it at every iteration of the loop, this is the same as computing t equal t plus I, and so on every time. Sorry, t plus equal x. Okay, every time. So what is the effect of the transformation? I'm basically replacing a multiplication with an addition. The multiplication is more costly, particularly if it is a floating point multiplication, with respect to the addition. It's more costly in terms of time, but it can also be more costly in the sense that we have less multipliers than others if the machine has multiple others. Then loop reordering. Loop reordering transformations are a category of transformations that take the iterations of a loop and reorder them to some extent. To which extent it's determined by the data dependencies, so the fact that data produced by one iteration of the loop are used in another. What is the goal of these transformations? Well, typically they try to put together nearby iterations that use near memory locations in order to minimize the thrashing of the caches. One easily understood transformation of this class is loop tiling. Loop tiling is a transformation that performs automatically block matrix multiplication. Okay, so it takes an operation on matrices that is typically performed in this working on cells in this order, okay, and instead performs it in this other order. And so on. Okay, so instead of using the typical loop structure where we have rows and columns and we iterate first on the rows and then on the columns, or the reverse, whatever you want, here we have broken the loop into each loop into loops, and we iterate on the outer and the inner part of each dimension of the matrix. It can be generalized to any number of dimensions, but it's typically performed on 1 or 2 dimensions. Okay. This has the same advantages that you can imagine for block matrix multiplication. If the matrix is very large, it won't fit into the cache, and therefore, by performing it blockwise, you reduce the amount of memory that is loaded at each time, and therefore it can fit into your cache or memory pages. It depends on the size of these elements. Then loop restructuring. Loop restructuring performs a more, on one end, more aggressive change of the way in which we iterate the loop, but without explicitly reordering the iterations. So all the loop reordering iterations change the order in which iterations are performed, and therefore they are sensitive to data dependencies. Whereas loop restructurings change the behavior of the loop, in the sense that the iterations are the same and performed in the same order, but the constructs that perform them are different. A simple example is loop unrolling, which, if performed fully, just replaces the loop with all the individual iterations. Okay, this clearly changes the structure of the loop because the loop is not there anymore, but does not change the order of the iterations. So what are the advantages of the two cases? So reordering enables some types of parallelization, or allows you to access memory in a more favorable pattern, which is not something that loop restructuring can do. Okay. Loop restructuring, on the other hand, may reduce the overhead of the loop itself, so the control structure. If you perform loop unrolling, you are trading off some code space, so the size of the code, for a reduction in the number of control instructions, which, if you have very small loops, it's useful. because a very small loop is dominated by its control structure, which is not performing useful work. You're doing only jumps. Okay, so in particular in those cases where you don't have hardware support for this kind of loops, which is typically the case of general purpose machines, then performing loop unrolling can reduce the overhead of the loop itself, and it also exposes some opportunities for other transformations. Why? Because for instance, reordering of instructions can only be done within blocks that are not interrupted by jumps, because if you reorder those instructions, they are already all executed. But if you reorder across a jump, maybe one instruction that you had to execute will not be executed anymore. So it's much more difficult to reorder across branches. That's why you have specialized transformation for loop reordering rather than just moving things around. Memory replacement. Loop replacement. Loop replacement is a full substitution of a loop with some other structure. This is performed on special patterns, such as vectorization, okay, where you have a loop that matches a particular size for which you can perform a vector instruction on your target machine, so this is fairly target dependent. And then you can remove the loop and replace it with special instructions that perform vector operations. Note that loop tiling, when performed on a single dimension, also can expose an opportunity for this transformation. Why? Because, for instance, here we have 6 cells, but maybe 6 cells are too much to fit your vector. If you break the loop in two, now the iteration space is not from 0 to 5, but is from 0 to 1, and inside this one there is another iteration space from 0 to 2. This fits into your vectors, so you have now a loop with two instructions where each is a vector instruction. Then you can unroll it and get just 2 vector operations. Memory access transformations, these are used to basically pad memory in order to optimize for memory banks accesses, or to replace vectors with scalars, or the opposite, depending on the needs of your transformation. Then, so these are all the transformations that affect loops. Then there are some transformations that are more baseline and cover, let's say, the removal of unnecessary computation that can be generated by other transformations, such as removing code that is not anymore reachable, or performing the propagation of constants, simplification of algebraic operations, and so on. Okay, we're almost there. So last set of transformations are those that affect procedures. These are important because in particular they include function inlining and function cloning or specialization, which are transformations that allow you to remove a call in or simplify it. Function inlining replaces a call point with the code that will be performed by the call itself. So it allows you to perform interprocedural optimization by removing the call and replacing it with its code, whereas cloning and specialization duplicates a function and then specializes it, which means that one copy is assumed to have fixed values of parameters with some useful values like 0, no? Where you can then simplify the code easily. If that particular value of the parameter is very common, then you can detect it before the call and call the simplified function and have it run faster. Okay? Okay, that closes our overview of compilers, and after the break, we'll talk about MLIR.
Thank you, Giovanni. Questions? Any question? Yeah.
You talk about the semantics of the language are not fully implemented. Well, the intermediate representation is not aware.
The intermediate representation knows nothing about it. Yeah.
Are there any examples of having intermediate steps of from the language going to a language dependent intermediate representation that you can optimize based on the semantics of the language and then feed that to
So you mean something where violating the semantics can allow you to optimize more in that
yeah,
sense?
exactly.
Well, let me think some example that is interesting. It's difficult to come about, but well, one simple example is what I mentioned before, the fact that we can perform transformations that um, violate the commutativity of the, so we by performing applying the commutative property, we can get some beneficial effects because, for instance, commutative plus associative, you can group things together and remove an instruction, but it is not guaranteed to produce the same, exactly the same value. Okay, so this is one. I remember that there were also some other things on the implementation of zero-length vectors, zero-length arrays in C, which are not exactly standard, but they exist. They are, let's say, supported in an unintended way, let's say. Things like that.
I was thinking kind of in some languages you may have aliasing rules for pointers
Yes.
very strong, and then in it, for example, in C you have to opt in for that.
Yeah,
Maybe having that step.
the aliasing, it's another major problem, which unfortunately in C it's not addressable, in the sense that unless you have the strict keyword, which is not part of the original specification for some reasons, you cannot, of course, safely perform some transformations. Those are not the type of things that are ignored freely, because the errors are major, so you cannot really, you don't violate that kind of semantics. Of course, where you have stricter semantics, the benefits are very heavy. Yeah.
Yep.
Other questions?
So, for someone that's not very familiar with the compiler world, is it fair to compare this intermediate representation to sort of the Java
Yes.
virtual
The
machine?
bytecode is an intermediate representation. It's one type of intermediate representation. The big difference is that it is an intermediate representation that is optimized for instruction, for execution on a stack machine, which is not typically what is done in a compiler, because it has no interest. So it is, let's say, optimized for interpretation, which
So,
was the original purpose of Java
so,
bytecode.
so we could have a future where any language could, in theory, move on to this MLIR or any other intermediate representation and then be compiled again for the target architecture or hardware?
In principle, yes. In principle, yes.
Okay.
So the IRs are in general designed to support multiple languages. So there is no reason, except the cost of doing it, why you cannot have a front end for language X for that targets LLVM or MLIR. Consider that actually implementing a language from scratch down to the target is much more costly than implementing a language down to LLVM or MLIR.
Thank you.
Thank you. So this part of the slides, I'd like to thank my student Michele Scuttari and also Massimo, who is there, will do the presentation for RLC. So, okay. MLIR. So what is MLIR? MLIR is essentially a multi-level intermediate representation, the associated compiler infrastructure. What does multi-level intermediate representation, now you should know, but what is a multi-level intermediate representation? Okay, we said that we have this picture where we want to move from several source languages to several potential targets, including domain-specific languages. Domain-specific languages are languages that are designed for particular purpose and typically have specialized constructs that are not very like the ones that you find in C or C++ or Fortran. Okay, in general purpose languages, okay, all general purpose languages are different, but more or less the semantics are the same. They express similar concepts. DSLs, not so much. Okay, you may have a DSL where derivatives are an operator, or DSLs where a neuron is an operator, and so on. Things that are completely different from classical programming languages. And therefore, the standard intermediate representation are not exactly amenable to building this compiler. The front end becomes overloaded with functionalities. You have to perform a lot of transformation in the front end just to match an intermediate representation, and then you don't get a lot of benefits out of the intermediate representation. What you would like, it's actually something like this, where you can deal with smaller concepts that are more domain oriented until you can get to a general purpose, let's say, intermediate representation. Why do you want to go back to that intermediate representation? Well, because that is very good for the targets. It's already suitable for the target, so you don't have to reinvent the wheel there. The problem is only in dealing with your strange DSL semantics, okay, which typically have nothing to do with the backend. So what you want possibly is that this IR1 is something that is very, very easy to match for your DSL specific semantics, so that it can match very easily the DSL. Then IR2 is a bit more say classical, and IR3 even more, until it gets easy to translate to the standard intermediate representation. So basically, we are trying to get rid of this strangeness that we find in the DSL semantics, but a bit at a time, not all together, because it's difficult. So that's the principle, behind the multi-level IR. I want an IR where I can get at the beginning very specialized semantics, and then I can transform them progressively into something that is more similar to a classical programming language, and therefore to also an assembly language, with the goals of having easy a framework that is easy to extend, it's flexible, can deal with many different types of semantics, and it has good performance and produces good performance in the code. So what does the MLIR framework introduce? It introduces a concept of dialect. A dialect is a grouping of functionalities that can be used to extend the system itself. So instead of having prescriptive semantics for operations, MLIR tells you make your own operations and you deal with them. Okay, that's the key idea. it has a generic textual format that can be customized for different operations, attributes, types, interfaces. Okay, this is an example of in the most let's say verbose form an MLIR operation. So you have here you can see the name of the result. Okay, this can have as a result that is named res, and is composed of two parts. These parts will have some types that we will see. The dialect has a name. This is basically a namespace that serves because multiple dialects can have operations with the same name. Then you have the argument or arguments. Here is the third element of input. Input is another variable, the result of another operation, which had 3 or more results, and you pick the third. Then you can have regions. Regions are blocks of code that can contain arbitrary stuff. So you can do whatever you can do in this within this operator. And then you have a set of attributes. This is a dictionary, so we have keys and values, and types. Here you have that the input has a custom type, and the output is a pair of two different, or actually the same, two elements of the same type. Furthermore, you have some debugging information. This is the typical location encoding. So you can ask MLIR to produce something like this that is relatively human readable. Okay. So what you can see is that we have custom types. So you can make up your own types. This is useful for domain-specific languages where the elements of your computation may be something different from what you expect in a standard programming language. Maybe they are not just int, char, and float. Okay, they may have something more specialized, like complex numbers or whatever. You have operators that are completely arbitrary. Okay, the morph operator does something. Doesn't matter what it does. It's your own problem. And these operators can also include other code. So they may be operators such as for, that includes a body. Okay, the body is not part of the operator itself, but it's a region within the operator. Okay, so you can define actually constructs that are fairly complex. Actually, they can be very complex. Okay. So the regions provide a hierarchical structure so that you have the operation itself, which performs something, but can contain other code. It can contain regions, but also it can contain regions can contain blocks. Okay, there is no specific semantics for this. They are just containers. Then the semantics depends on the semantic of the operator. Okay. Let's look here at an example where we have a block. Here we have a function that contains a while. Okay, so a function contains a region that is its body. Okay. Clearly, the function has a semantics per se. It does something, the prologue and the epilogue of the function, but the majority of its work is performed in the region, which in this case contains a while statement, which has multiple regions, each with one block. These regions perform the condition and the body of the while, essentially. Okay, so here we have the region, the block, and then inside the operator while you have two other regions that contains each one block. We can have some specific regions that have properties. In particular, we can have regions that are able to check automatically the uses and definitions of SSA values, static single assignment values. These are regions that behave according, they are called SSA control flow graph regions. Okay, it means that within those regions we are guaranteed that the use of a value follows the definition. Okay, so that the ordering is that the one that you would typically expect in correct code in a typical programming language. This is fine for programming languages. However, there are also declarative languages where uses and definition may be mixed freely, and these are the graph-like regions. Those graph-like regions allow freedom in reorderings. So you can express, for instance, parallel computations or computations that are not ordered. For instance, if you think equations where the left-hand side and right-hand side of each equation are true all at the same time, they have no ordering, those can have this kind of semantics. Okay. Dialects. There are many dialects. Okay, but when I say many, this is a partial view. Nobody really knows how many there are because it's evolving continuously, and the classification of such dialects is also very, very complex. This is an attempt that was done in the MLIR community, but it's really not complete. However, it shows the complexity. What we can highlight, I think it's very difficult to see, but if when the slides will be shared, you can read it. However, the violet blocks, this represent the LLVM-IR. LLVM-IR is included inside MLIR as a particular dialect. Okay, that is the equivalent of a backend dialect for MLIR. There is also SPIR, okay, for compiling for GPUs. As an alternative, let's say, output dialect. Then there are core dialects, which are the ones represented in this light blue color. There are external dialects that are basically those that are developed by front-end developers to add a new language. You can't see, but I can tell you that most of them are for AI, TensorFlow, TensorFlow Lite, Torch. These are because these languages, represent constructs that are typically not found in programming languages, so they need their own semantics. They develop their own languages. Note that even though these are all AI frameworks, they use their own IRs. They also use and share the use of a number of core elements, the ones in light blue, and new elements that have been added recently, which are in green, and there are many, of course. In particular, I want to highlight the presence of a tensor dialect that is specific to represent operations on tensors, so on non-variable matrices. that are useful, of course, for AI, but particularly useful for reasoning on such operations without having the need to specify where they are in memory. Okay, so there are then transformations. The arrows lead from a higher level dialect to a lower level dialect. So dialects are progress from higher level at top to low level at bottom. At some point, you can transform a tensor dialect into a memory reference dialect. So get out of the tensor representation and map in memory in order to obtain a code that can be compiled by LLVM. There has been an attempt to classify these dialects according to the following structure. We see a divider between tensor dialects and buffer dialects. Tensor dialects do not represent memory areas directly. They represent values. Okay, so they try to do the same thing that is done in the classic compilers with virtual registers. They are doing it with memory. They are representing these arbitrary values that are not located already in memory, and they are just read-only. They are written once, and then they will be dropped. And then they perform something similar to register allocation when they try to map them in memory, minimizing the memory usage and memory movements. Buffer dialects use the classic memory allocation, so they map variables in memory and therefore move towards the target languages. There is also partitioning between payload dialects and structured dialects, where the idea is that structured dialects represent more the structure of computation, so the control flow, whereas payload dialects represents operations. Okay, so all the AI things are payload dialects, and the structured dialects are used at a lower level to perform transformations on the code itself. So to map another intermediate representation onto something that exposes a particular structure, and then you can transform that structure and move out of this particular representation. So they are representations that are only useful to allow an easier implementation of transformations. Indeed, you can see that these elements don't have a direct output. They move back into the buffer payload quadrant. They come from this part of the picture, and then they go back. As a disclaimer, the picture is not fully precise. For instance, tensor is false in here, but actually should be a bit higher, because it's really a tensor payload dialect. Some other aspects that are worth mentioning about dialects is that there are some machine-specific dialects. Why? Because in many cases, machines provide some particular types of operation that can be optimized through dedicated idiom recognition. So vectorization is the typical case. There are dialects for instance, the ARM Neon, if I remember correctly, yes, and the GPUs, for NVIDIA GPUs, for AMD GPUs, and so on. Okay, this is more or less what I had to say. Yeah, so the classification is that kind of structure. Yes, here there is also within the structural dialects an identification of higher level structural dialects that try to expose patterns in the program that can be identified and transformed. Iterations, so that expose loops to perform things like tiling easily, And finally, some programming model specific dialects. There are dialects specialized for instance, OpenMP that are or for async and so on. And finally, platform specific dialects. So MLIR is not a language, but rather a way to build new IRs that can be combined together. So you don't use one IR on its own, but typically you combine multiple IRs in order to build your program. So for instance, your IR might have only arithmetic operations. Okay, you can't use it on its own because you don't have function calls. But then you can pick the function dialect, which has all the tools to build functions, and you just plug it inside those functions your arithmetic operations, and that's all. It's also not a compiler, but rather a framework. So it's a library that allows you to manipulate this intermediate representation, and then by manipulating the intermediate representation, you can build a chain of transformation that lead from a source IR to a target IR. MLIR, of course, it's used and it sees a lot of use to build AI applications. It is supported by all the primary tools, TensorFlow, PyTorch, and there is also, and it was the first, an ONNX compiler front-end for MLIR. There are also, however, not only machine learning representation and languages, but also programming languages such as Mojo. Someone was mentioning it before. Fortran, Flang. This is interesting. Flang, there were two Flangs. One was an attempt to build a compiler using LLVM, which sort of petered out because it was a lot of effort, and then it was redone in MLIR successfully. There is PyLIR for Python. There is Polygeist, which tries to implement a language specialized for polyhedral transformations. And finally, Silang. Silang is very work in progress. The problem there is likely that the effort is significant, and there is already Silang for LLVM, so the interest is not so big. But more interestingly, there is space and room for a number of other languages, including descriptive languages such as the circuit dialect that is used to describe circuits, and Marco, which is a dialect that I will discuss in a minute. It's our, so that is the theory. Now let's look at a couple of things that we have done with it. Okay, we've used MLIR to build a compiler for Modelica. Modelica is a language that represents systems of differential equations. So consider electric network. You can represent it as voltage and current, and then you can build a model of the capacitor which has some equations. Okay, those equations have the equal sign that has the meaning of the being the same value at all times. So in a simulation, at all steps in the simulation, the left-hand side and right-hand side should be the same. And there is an operator derivative that computes the derivative of a variable in time. Okay. So these are equations. You can build them, however, in loops to build large-scale systems. So you can have arrays of variables that are to which you can apply the derivative operator, or you can put them, you can connect them with equations or connectors. The loop is a compile time loop. It generates a number of equations. Here, 3 lines of code generate 100 equations, so the size of those systems can be significant in the number of equations. We use MLIR with a couple of new dialects. One for the Modelica language and one for IDA, which is a solver. So it allows us to interface with a solver of differential equations. Plus, we use some classical dialects, functions, memref, and arith, and LLVM to generate the code. We also have another project. This one is a new language, so it showcases how you can implement a language from scratch using MLIR. But here we have the author, so Massimo, I come here and I leave it to you to discuss rulebook and to maybe also give us an example.
So as we saw before, actually, in the past I worked on the Modelica compiler too. So it was kind of a group effort, and the lesson learned from the Modelica compiler, then we applied it to RLC. And RLC is a new language. So in the case of Modelica, we had very large constraints about what we could do. As in, a standard was already defined, and so you just had to read the standard and try to implement it. While in the other case, MLIR was very important for RLC, which we'll see in a second, because what MLIR allows is to do quick iterations between the design space of a language and say, okay, it takes me only 20 lines of code to implement a new operator. This is not an exaggeration. For example, the patch which introduced the continue statement that lets you continue or break statement, it's probably around 50 or 100 lines of code from the parser all the way down to being translated to LLVM-IR. Input is RLC. RLC is similar to some degree. It is still a DSL, such as Modelica, but what lets you do is, I hope it's big enough because I was in the back and I saw that I couldn't read anything. And what it lets you do is that you can declare, this is an example of tic-tac-toe, that is implemented as if, as you would implement it in a computer science 101, where you say, the rule of tic-tac-toes are, there exists the board, while the board is not full, you can mark a piece of the board, and while the board is, which means the player provides X and Y, and you must make sure that X and Y are between 0 and 3, which is the bound of the boards, and the slot of the board at X and Y must not be set. If that is the case, then you can set that slot of the board, and then you can say, if the game is done because there are 3 in a line, then you are done. Otherwise, you change the player, you go back to the loop. And if you read it, this is exactly what is written there. And what the compiler does is that it translates this program into an optimized library, where this is being exposed as a class, as in there is a class that represents the simulation, in this case, the simulation of tic-tac-toe. And then you get the methods, such as mark, which are the actions that let you operate on the simulation. In this case, they let you mark the slot on the board. And what you get then at this point, since the simulation fully describes all the transition possible in the language, since the program describes all the possible transition of the simulation, is that you, for example, are able to throw a machine learning stuff on it completely unassisted, as in you only provide this file, and then you invoke a single command, a single program, which will inspect the program, figure out what it can do, and then run machine learning on it. So, oh yeah, and to see the same architecture as before, what we have is a custom dialect, which is the one for RLC, which is lowered to the standard dialect for LLVM, which and the other dialects, such as the ones to express to use memory, and the ones who talk about the target architecture. And then on the side, we have a very small dialect to express Python wrapper, and then from the RLC, from RLC, and then what we can do is omit the the file object that represents the library that includes all the rules, and then the wrapper to make it compatible with machine learning stuff. Okay, we have the publication. I don't know if we.
Oh, we can skip that.
Okay.